All right, we're going to look at, now that we've done antiderivatives, the next section in the book is now getting into more about what we're going to use antiderivatives for. So in first quarter calculus, we used derivatives and we saw that one of the main uses for derivatives is to find the slope of a tangent line. And we saw lots of examples of being able to find the slope of a tangent line, how that could help us solve different problems, right? We did optimization problems, we graphed functions, and we're able to use the derivative to find maximums and minimums for different functions. So one of the uses we're going to find out with antiderivatives is to be able to find the area under a graph, okay? We won't be using antiderivatives for that, to do that right now, but we will soon. So right now, we're just going to get practice figuring out, estimating the area under a certain function. So we're going to find the area, or estimate the area, under f of x equals root x over 0, 16 on the x-axis, okay? And we're going to use a regular partition of 4 rectangles. So what does that mean? A partition, when you partition a room, you divide it up, right, into smaller pieces. So what the partition is referring to is this interval. Okay, I might as well show a little bit more here. From 0 to 16, we're going to partition this into 4 equal parts, and we're going to put some rectangles underneath the curve, or possibly over the curve. Because in my first scenario, we're going to use 4 rectangles and we're going to use right endpoints as sampling numbers. Okay, I'll explain what that means in a second. So first thing, I would have drawn this curve. I would divide from 0 to 16 into 4 equal parts. Now the width of each rectangle, or each subinterval is another way of saying that, is, we call that delta x. And your formula for delta x, it's traditional, the left-hand number, we're going to call that A. The right-hand number, which is 16, we're going to call that B. To figure out the width, we want this total length, which of course is 16, and then we want to divide that into 4 equal pieces. So in general, to find the total length, you're going to go B minus A and divide it by N. N would be the number of rectangles you're using. So in this case, we have 16 minus 0 over 4, which is 4. Okay, so the width of each rectangle is 4. Now, what's meant by sampling numbers, that term, since this problem asks us to use right-hand endpoints, if we take this first subinterval from 0 to 4, the right endpoint is 4, which we call C sub 1. We're going to use that as our first sampling number to determine the height of the rectangle. So this would go up here and go across, and that would be the first rectangle. For our second subinterval, between 4 and 8, we're going to use the right endpoint as our sampling number. So that's C sub 2. I know the writing's a little bit small. C sub 2. Whatever the height of the function is at that value, we're going to come back and make a rectangle over there. C sub 3 would be 12. That becomes a rectangle, and C sub 4 will be the last number, 16. We make a rectangle. Ultimately, we're interested in the area. So what is the area of a rectangle? It's just the width times the height. So if we take the first rectangle, its width is delta x, and its height would be determined by f of 4. For the second rectangle, it's delta x times f of 8, and so forth. Now notice delta x is the same for all of these. So to make the calculation easier, we can actually factor out the delta x and then just multiply it by f of 4 plus f of 8 plus f of 12 plus f of 16, which are found by just plugging in 4 into my function, which is the square root function. And of course, delta x is 4. So then my approximation would be this, which if you get out a calculator, you can figure out what that equals, okay? I'm not gonna waste the time right now. Now, this is called an approximating sum or also a Riemann sum. Riemann sum, when you're using rectangles to estimate the area under a graph, then it's called an approximating sum or a Riemann sum. Now, you can tell from this estimation, whatever number I get here, it's clearly an overestimate of the actual area under the square root curve, right? These rectangles are way above the actual graph. So in this case, this is an overestimate of the actual area. Now, another way to get an estimation, we used right-hand endpoints to estimate the area in part A, and we saw that was an overestimate. I could also use left-hand endpoints. And so what that would look like, here's my square root function. I have the same delta x. I've got 0, 4, 8, 12, and 16. But now I'm going to use for each subinterval the left-hand number as my sampling number. So I'm going to use 0. And of course, I don't get any height for that because the value of the square root of function at 0 is 0. For my second rectangle, I'm going to use the 4, my left-hand endpoint, and that becomes the height of my rectangle. My third rectangle's height is determined by x equals 8, and then x equals 12. So before we even do the calculation, clearly this is an underestimate, right? There's all this extra area that we're not counting if we use left-hand endpoints in this situation. And then to actually find the area, once again, I would factor out the delta x is the same for all of them. And then you would just do f of 0 plus f of 4 plus f of 8 plus f of 12, and you would get an answer for that, okay? Now, right-hand endpoints in this case give you an overestimate. Left-hand endpoints give you a pretty bad underestimate, right? That's not very accurate. So what's another choice I could do? If I stick with 4 rectangles, I could kind of split the difference here, right? Rather than using a left-hand endpoint or a right-hand endpoint, what if I choose the midpoint of each subinterval as my sampling number? Okay, and you can tell by doing that, if you look at your first rectangle, this part on the left overestimates the area, it's above the curve. This part right here underestimates, and you can tell they're pretty close together. So the amount we overestimate by kind of is similar to the amount we underestimate by, so these could kind of cancel out. You can tell because the graph of square root of x is curving downward that this overestimate is a little bit bigger than the underestimate. So we're going to get a slight overestimate for this approximation. But it's a pretty good estimate, even with only 4 rectangles. It's the same formula, right? To find the area of rectangles, you're going to multiply the width times the height. The width is the same. The only thing that's changing is the numbers we're using to find the height of each rectangles, which are your midpoints, which I know you can do the math here. You're going to be using 2 and 6 and 10 and 14 instead. And that'll give you a slight overestimate for the actual area. Yet another option, just to show you have lots of different options when you're estimating area, is we could use a non-regular partition. What a non-regular partition is that the widths of each of these rectangles, they're not equal to each other, right? They're not the same. Now, why would you do that? Well, usually you would want your rectangles to have the same widths, but there is maybe a good reason for this particular case to use a non-regular partition, because my function is the square root function. And notice the numbers I'm using, 1, 4, 9, and 16 as my sampling numbers. Those are numbers that have nice square roots. And so if I wanted to get an idea of what the area under this graph was and I didn't have a calculator, this might be an option, right? because I can take those square roots pretty easily. So I'm using right-hand endpoints, but I'm using these special chosen sampling numbers here. So I'm going to get an overestimate. One term that we're going to start to talk more about is called the norm of the partition. And the notation for that, P is partition, and we use a double absolute value. And that's defined to be the width of the widest subinterval. So in this case, this particular case, my widest subinterval is right there, right? That's certainly wider than any of these other rectangles. And so that would be 16 minus 9, which is 7. So for this particular problem, the norm of the partition is 7. Okay, and then to actually find the area, we're doing the same thing. Although here, we have to multiply. We can't factor out a delta x because the widths are all different. So this 1 is the width of my first rectangle times f of 1 is the height. The next width is 3, right, between 4 minus 1 times f of 4. This width is 5 times f of 9, and then 7 times f of 16. And actually, here's the one I actually did calculate. If it's because it's easy, you will end up getting 50 as an estimate for the area, which again, it's an approximation, right? It's not super accurate, but at least it's an idea of what the area is. Finally, I wanted to give you a sense, why would we do this? Why would we care about the area underneath a curve? Sorry. Okay. So suppose that the function is the square root of t, and it's giving us the velocity of an object at time t in meters per second. So maybe this is, I like to use the example of a runner because I like to run. Maybe this is my velocity. As I start my run, I'm picking up velocity, right? I'm going faster and faster and faster over time, and t is measured in seconds. Well, what does the area under the curve mean? Well, if we take one of those rectangles, let's just use this one as an example. What is the area of the rectangle? Well, this width would be measured in seconds, right? And the height would be measured in meters per second, And what happens when you multiply area, when you multiply meters per second times seconds? The seconds cancel out and we end up just in meters. And the way you could interpret that is distance. Okay. So the area under a velocity graph actually gives us the distance traveled. So you could interpret the area of this rectangle right here as an estimate of the distance the runner travels between 8 and 12 seconds. And you could interpret the area of those 4 rectangles as an estimate for the distance traveled by our runner from the beginning of the run to 16 seconds later. Okay. And it's the same thing we've been doing. You take your delta, in this case, delta t times f of your sampling numbers. And okay, here I'm just showing again that that's, oh yeah, one other thing. We'll talk more about this in the next video here, but anytime you're adding things, we can also express that with a sum. This is a summation sign. And so the way a summation works is the bottom number is just your counter. So like if I had C sub 1, C sub 2, C sub 3, C sub 4. So in general, I could call this f of C sub k. I'm adding these together, where k becomes 1, 2, 3, and this tells me to stop at 4. And I take all those values and I times them by delta t. So this is just a way, and we're going to use this a little more frequently to denote anytime you're adding up a bunch of numbers, you can write it in summation form. Okay. And then finally, what I've already stated, but here's it written out. This particular approximating sum estimates the total distance traveled by an object or a runner that has a velocity of root t over that interval.